Hello, this is Miss Moore, and today during chemistry we're going to discuss standard heat formation. Truthfully, we're still going to be talking about enthalpy or change in energy, delta H, change in energy. It's just another way to calculate change in energy. So today's essential question, what is standard heat of formation? Or it's also known, by the way, as standard heat of enthalpy. And how is it used to calculate enthalpy? So here we go. Calculating enthalpy. Remember, this is a review that delta H is known as change in enthalpy or change in energy. So delta H is really the difference in enthalpy or energy of the products and the reactants. And what we're looking for is the overall change in energy, right? So we're looking for the overall change in energy as a reaction is occurring. And if the overall change in energy is negative, that means we end up with, I guess you could think of it, excess energy is released, and that would be an exothermic reaction. And if the overall change in energy is positive, we're gaining more energy than we're losing, which means we're looking at an endothermic reaction. All right, well, there are several ways to calculate enthalpy or change in energy of a reaction. One way that we've already discussed is to look at bond energies. And remember, we looked the numbers up on a data table. After we drew out and figured out how many bonds we had, what types of bonds, we would look up the energy on a data table for each of those bonds. But bond energies on those tables was the energy needed to break bonds. Okay, so and most of those energies were positive because often energy is needed to be absorbed or to use to break a bond, right? And so they were mostly positive, most of them. And the numbers on the data table then, since we're breaking bonds, where are bonds being broken? The data table is talking about the reactants, right? And we had to change the sign for the products because on the product side of the reaction, we're actually forming bonds, which normally leads to a release of energy. A second way to calculate change in enthalpy or delta H is to calculate heat of formation, which we symbolize like that. So standard heat of formation. Standard heat of formation, or delta HF, F for formation, is the change in enthalpy that occurs when 1 mole of a compound is formed from its elements at a standard state. By standard state, it usually means like a non-changing state. You can think of it like 1 atm, and it's usually about 25 degrees Celsius. But basically, we're talking about a non-changing state. All right, so let me kind of give you an example of what I mean by this part right here, when 1 mole of a compound is formed from its elements at standard state. Okay, so an example would be, say I wanted to make 1 mole of water. What's water made out of? Well, it's made out of hydrogen and oxygen. Now, in its standard state, hydrogen is diatomic, right? So it'd be H2 plus O2. And then if we were to balance this, we would need to put, we would need to put a 2 here and a 2 here. However, we now have 2 moles, right? So that isn't going to work. So another way to balance this would be to say we want 1/2 of a mole of O2. Okay, so when we look up our numbers, we're looking at how much energy did it take to produce or make this. That would be our standard heat of formation. So let's try another example real quick. We could also have something like, let's say we're looking at for the standard heat of formation of carbon dioxide. Well, what's that made out of? That's made out of carbon, and at a standard state, elemental carbon is just a single carbon, and oxygen. And oxygen, standardly, is diatomic, so it would look like that. And the numbers we would look up on our table for the standard heat of formation, again, would be the formation, the energy it took to form this. Now, unlike our bond energies, for most compounds, the standard heat of formation is negative. Why? Because often, not always, but often, when you're forming bonds, the overall reaction will end up being, whoops, I was going to write endothermic there, exothermic. Okay. All right. So a couple things you need to know is that the delta HF for an elemental compound in its standard state is 0. So what do I mean by an elemental compound in its standard state? Well, from the example above, elemental compound carbon is commonly monatomic or by itself. Its delta H would be 0. H2 would be 0. H would not be 0 because that is not in the standard state. It would take some effort to get there. Okay, so no. Let's see what else. O2 would be 0. Cl2 would be 0. Sodium, 0. Okay, so the delta HF for an elemental compound, whether it's monatomic in its natural state or diatomic in its natural state, is going to be 0. All right, so to calculate standard heat of reaction, or to calculate change in enthalpy using standard heat of reaction data, you are going to use the formula, or the reaction, the formula, I guess, equation, right here. The change in enthalpy, and this little symbol there indicates that you're using standard heat of formation, okay, equals the sum. This thing right there is the sum of the standard heat of formation of the products minus the sum of the standard heat of formation of the reactants. So, real quick, because I don't want you to get things messed up, why is it products minus reactants? Well, because standard heat of formation, right? Formation. The numbers are standard heat of formation. Products are formed. Reactants, on the other hand, they're not being formed, right? And during a reaction, they're being broken down, so that means the sign needs to change. So you need to have a sign change. So you can look at it one of two ways. It could be the heat of formation of the products minus the heat of formation of the reactants, or it could just be sum them all up, but you have to change the sign of the reactants. Okay, so this is the equation we're going to use. Oh, by the way, you don't have to have this memorized. It's on your AP Chemistry reference table, and it should also be on the AP Chemistry reference table when you actually take the AP exam. Okay, so I have some example data tables that you will be looking at. A real one would have a lot more information on it, but I just have this little one for here. Okay, so let's now try a practice problem. So here it is. Calculate the enthalpy change, delta H, of the following reaction using the standard heat of formation data. So we have C2H4 in the gas form plus 3 oxygens in the gas form producing 2 gaseous CO2s and H2O liquid. And we have a little typo here, a major typo here, I guess. This needs to be 2 H2O liquids, right, for all this to balance out. Yeah, okay. So, how do we go about doing this? Well, the first thing we need to know is we need to know the standard heat of formations of each of our compounds. So let's look that up on our table. Let's start with C2H4. Let's see. C2H4. Here, do you see it? Anybody see it? Up there it is. Right there. And by the way, these are in kilojoule per mole. So we have 52.3 kilojoule per mole. Okay. And then O2, remember O2 is an elemental compound in its natural state, which would be diatomic. So he's going to be 0 kilojoules per mole if you want. Let's see, next, let's change color for the products. We have carbon dioxide in the gas form. That's important. It's not a good color, try this one. Carbon dioxide in the gas form is right here. We have negative 393.5. Kilojoules per mole. And lastly, we have water in the liquid form. It's bottom of this one right here. Negative 285.8. Kilojoules per mole. All right, so now what we need to do is just basically plug and chug, remembering that the equation that we're going to use to calculate the heat, the change in enthalpy using heat of formation, it's the sum of the heat of formation of the products minus the sum, the heat of formation of the reactants. And remember, for the reactants, you can do one of two things. You could either follow this exact formula, or you can think of it as, I write a different color, as adding the products, but you have to change the sign. Whichever, it doesn't really matter. All right, so let's do this. So our products need to go first, right? And our products are the ones in orange. So these guys right here. So we're going to have delta H equals, you will note there are 2 carbon dioxide. So delta H equals the sum of, let's see, 2 times negative 393.5. Added to that is, let's try that again, 2 times our heat of formation of water, which is negative 285.8. And then we're going to take all of that and subtract, in this case, our C2H4, which is 52.3 kilojoules per mole. I've been forgetting to write that down. Plus, if we want to just be consistent, we need to add 3 times 0, which is kind of a waste, but that's okay. And then just plug and chug. So when I put all of that in my calculator, I came up with negative 1410.9 kilojoules per mole. If we want to look at sig figs, being that we're doing adding and subtracting it and stuff, we're looking at digits after the decimal. We'll kind of ignore that 0 there. And everybody has 1 digit after the decimal, so this would be my final answer. And because the change in enthalpy is negative overall, that would mean this kind of reaction is, shout it out before I write it, exothermic. All right. This isn't really too difficult. I think the hardest part about doing these, figuring out enthalpy using standard heat of formation is remembering that is comparing it to bond energy. Keeping in mind that when we're talking about bond energy, we're talking about the energy to break bonds, which means we have to change the sign of the products because the reactants are the ones breaking bonds. When we're talking about heat of formation, when we look up those numbers, again, those are heat of formation, so those numbers would be coming like you'd think of them more as the products, which means we need to change the sign of the reactants. All right, folks, that's it for today. Have a good one.